intensity, that's measured in watts per square centimeter, intensity, spatial peak, and temporal average. And for the cavitation, it's the functional, maximum functional, that's stretching pressure. And we must know other things as well, but these are the basics. Next, please. However, for yourself as users, these intensities, precious things are not applicable in daily practice, really, or hard to apply, and therefore these indices have been developed for the user, for the operator, as a guidance. Now the indices, there are two. It's the mechanical index and the thermal indices. The mechanical index tells us something about the probability of cavitation. The thermal indices are there to tell us something about the heating up the tissues. Mechanical index is defined as you see here, and that's the peak gravitational pressure. And both these indices will appear on your screen. Somewhere on the screen there is this index written, and it changes as you change the controls of the machine. The thermal indices are numbers, and you see there are three of them, three sort of flavors to them. Soft, for soft tissue, for the bone in fetuses, and for the adult bone, that is for, let's say, transcranial Doppler. Although it's a gross idealization, but you ought to know that the number you get there, like number 1.3 or something like that, that number really means a theoretically calculated under certain conditions and limitations, calculated increase of temperature in Celsius in situ. That's in the body that you are just, in the patient that you are just scanning. So if you get a number of 2 in the screen, it means that that part that you're looking at is going to heat up by 2 degrees centigrade, although it's a conservative estimation and it has a lot of limitations. So you shouldn't take it literally, but it's a guidance. And if you remember the slide which told us that we should not heat up basically more than 1.5 degrees Celsius above normal body temperature, that means that we should tend and want to have our thermal index whenever we were less than 1.5. That's what we normally want to do. Next please. Now this thermal index can appear on the screen, and you see here, this is thermal index for soft tissues, and it says at this particular setting, whatever it was, it's less than 0.4. That means that here the temperature is going to increase by less than 0.4 degrees centigrade. So we're looking at that. But that we have in some machines. In modern machines, new machines, and in the machines that are well, higher class, let's say, middle class. In older machines you don't have this, and it will have consequences on the regulations that we'll see later. Next. Now, what can be displayed on the screen that pertains or is in some way related to safety? All these things here, like transmitter power, it could be in milliwatts. That is something, because with some calculations, and you've seen some of them in the slides yesterday, one can calculate some real physical values. Sometimes you just have percentage, and it will tell you 100% or 80% or something of the sort. And from, let's say, from today on, try to look at the slides that you are getting in various lectures, in congresses, and so on, and try to look at the percentage or that in the screen. And you will find that, by and large, people simply ignore all these things, and you will always see 100%. Nobody cares. But you should care. Or thermal indices could be as well, and the mechanical index could be or can be displayed on screen, and that's related to safety. Next, please. Now, there are certain terminology conventions that you may not know, and that's important for us in these discussions. One is something called ODS, Output Display Standard. There are standards, there are international and national standards that define what and how it should be displayed on the screen, so that we can compare machines. And there is a principle, this LALU principle, which is just a normal common sense principle, which means that we should use as low as reasonably achievable hazardous agents, whatever it is. This has been developed for, as a philosophy, for ionizing radiation, X-ray, and so on, isotopes. But it applies to anything. What it really means is that sometimes you must decide whether what you're doing can do some harm, but the overall benefit for the patient is better than the harm. And so that the overall net result is a benefit for the patient. We know that all that. When somebody comes with a broken leg and you do the X-ray and you adjust the bone and put everything together, you're irradiating that patient, and the patient can develop something later on in 10 years, leukemia or something. But in fact, when you take the whole sum and sum it up, it turns out that by and large, for the majority of patients, it's a benefit, and that's very good. Next, please. Now, this is statistics of real scanners that you can buy, like your scanner here. Somebody, Henderson and Ducken and Martin, they went around and they measured real actual parameters. And it turns out that the fractional pressure, that this has to do something with cavitation. You see that it has a tenfold ratio among machines, but it really does not depend much on the kind of application that we are doing. Not so for thermal mechanisms. For thermal mechanisms, you see that the pulse Doppler on average is more intense than everything else. And that's why when looking at the safety aspects, we should basically first look at the pulse Doppler application. Now, if that is safe, then the rest will probably be safe in a particular machine. But you see that these two ranges overlap, so that the lowest in pulse Doppler is much lower than the highest in beam mode scanning. So it's not that the pulse Doppler is out of limits, or we don't want to use it, but we must see what our particular machine does. Next, please. Well, these are the laws that go in the United States and are going or are being accepted throughout the world. And you see that there is something, a magic number, 720 milliwatts per square centimeter, which really means that if we have everything on screen, if we have the thermal and mechanical index on screen, or we can have it, then by the present American regulations, which, as I said, are going to be accepted or are being accepted by the rest of the world, then we may use 720 milliwatts per square centimeter. Our machine can have it. Ophthalmology is an exception for many things, and that includes the mechanical index. But if our machine, whatever ultrasound, can transmit less than 100 milliwatts per square centimeter, then you don't need to have any label. And that's the fetal heart detectors. They will typically have much less than that, and they simply don't have any label because they are in a safe region by themselves. Next, please. So, this is what you should have on your machines. If your machine is made in such a way that it does show the indices, the thermal indices, the mechanical industry, then you may have, except for ophthalmology, 720 millivolts per centimeter. On the other hand, if a machine does not show all these parameters on screen, then you may have, for obstetrical applications, less than 94 millivolts per centimeter. That's a regulation. It's a strange table, this one, if you think of it. It's very, very strange. Actually, I think that in these papers that you were given, that was all written before I had all these data, so I don't know whether there's any reference to these things. But anyway, if you think of this table, I'm sure you'll see that something is wrong with that. Try to think of it common sense or philosophically, whatever. How can the intensity that's transmitted into somebody's body depend on what is written on the screen? How's that? Don't you see that this is not logical, although this is logical? Actually, it is logical, but there is a hidden logic. This does not mean, this here, does not mean that if we have a number on screen, then our machine is less hazardous and we can easily insunate our embryo with 720 millivolts per centimeter. If that little number is not on screen, then we may not. No. What it really means is that there is no proof whatsoever that this is hazardous for fetuses and embryos at all. But we have 2 generations of women who have been scanned with ultrasound and without any detectable malformations to their children or grandchildren, only with that data on hand. Because that's what we had in the early 70s and late 60s of the last century. So grandchildren are being born now. No problem with that. So, if we are totally blind, and we have been totally blind until up to 3 years ago or something, or more, then we know that this is harmless. But there is no proof whatsoever that this does any harm, but then we have to wait another 30 years to put this number into here with all the studies. So that's why we have this. Now, if you have this here, and it turns out that somebody comes up with a credible result that you may not use 720 watts per square centimeter, millivolts per square centimeter, but you should use 380. Then, if you do have this guidance, if you have the indices displayed on the screen, you can control yourself. If, on the other hand, you are totally blind, if you have a machine that doesn't show you anything, then it must be safe right from the beginning. And we know that this is safe. That's why a blind machine can have only this, and a machine with some indices may have all that. So this is the law in some detail, and we shall not go into detail for that, because if we start that, we need another 1 hour of going into very many details. All this are just tables from a 60 pages standard, and it's a mathematical text, but it's all there, and so I'm just showing you that it's being taken care of in much more detail than I told you with the previous simple table. Next, please. And it's explained in a lot of detail and defined and limited in a lot of detail. Next, please. So, the standards are there. You don't have any possibility to do physical measurements. What should you do in order to work as safe as possible? This. Just do what's written here. One thing, you should work with the smallest possible power and highest possible gain. Of course, you increase the gain until you get the noise in screen. Then you reduce it a little bit. You don't want to have noise in screen. But if you do it this way, that you reduce the power, and there is a control measure, If you do that, then you will use less than maximum power under all conditions, but that one when you actually need the maximum. Of course, there is no place for frivolous application or use of ultrasound. It's not a joke, it's a medical examination. So just do it as a medical examination. If you think it has a benefit, it can have benefit for the patient, then do it. If not, for pure curiosity, absolutely not. And of course the machine must be adjusted properly. Frequency and focal zone, everything must be adjusted properly. You should have it as it should be. Because if you adjust this properly, that means you use the frequency that is applicable in that particular case, then you will use less energy and you will be done with the examination faster than without it. Next, please. Now, there have been a number of papers that compiled hundreds of studies that have been done throughout the world and who tried to somehow sum up, and this is one of these summing ups by credible people, that is Stuart Campbell and Lawrence Platt. And these are the recommendations. When you look at this, you see that these people, and there are credible people, that they suspect that there might be something to this safety. We don't know anything, but there might be, and we should be on the safe side. Especially in these litigation societies like the United States and UK. Next, please. So what's the present opinion? This is my opinion. But I think it goes without us. There exists a potential risk. It does. Because we know that there are mechanisms that could harm. Could. But there is no proof that under the condition that we use the standards and the limitations outlined before, that there is any biological damage. So as long as we keep our machines within the standards, that means we buy the machines that are credible, we may use ultrasound whenever we deem necessary. Whenever we deem necessary. Next, please. There are some things that we should never know. When we say that something is harmless, or mostly harmless, or something like that, what we say is that as far as we know, there is no harm. Now here are two calculations that show you that there are things that we can never know. If you have something like 2.5% of prevalence of something, whatever, natural malformations, and they, for whatever reason, increase by 3%, then with a thorough study of 2,700 patients, you will be able to detect that this increase happened. So we know that it did happen. However, if the prevalence is much lower, like 1 in 1,000, 1 in 1,000, if that increases by 10%, you will need to have a control experiment of 250,000 patients to detect this, which really means this cannot be detected. There is no way to know it. So you see, when we say that something is safe, then what we say is that there is no way to tell that it's not safe. It may add something. For example, you could do this study during 10 or 20 years, but during these 10 or 20 years, everything will change. The soaps will change, the detergents will change, the cars will change, there will be new colors, new fabrics, everything. New medication, a new food. And you will never know whether the result you get after 20 years is due to whatever we've been doing, ultrasound or something else. So, this is the end of this. There are things that we will never know. But it's safe. It's safe. Just go on doing it to do it properly. One of the, just the practical, thank you, you can shut that down. A practical advice is this. Does it have FDA approval? The machine that you're buying, does it have American approval? Because Americans are practical people, although theoretical things are not known to us. Some of them will not be known for years. They did define rules. They gathered committees both from manufacturing industries and users, that's American Institute of Artisan Medicine, AUM, and they defined these rules that we see here. So, if it's safe for the United States, it's probably safe. No, it's safe for everybody else as well. And so, if you don't want, or you cannot go into details with all those watts per square centimeters, thermal indices, whatever, then that's the simplest question to ask. Is it FDA approved? If yes, okay, then it's safe. If not, actually the advice is don't buy it. Don't. Because sooner or later somebody is going to be in trouble. You or the patient or whatever. Simple. Thank you for your attention. So, this is this. And now we have to so we must know that the characteristic acoustic impedance of soft tissues is in a range of 1.5 megarad, and they're around plus minus a few percent. But the bones have a much higher characteristic acoustic impedance, about 7, 8, and that the air gases in the body have a much lower characteristic acoustic impedance, and for that reason we can't look into those structures filled with these other media. On the other hand, the refraction depends on the speed of ultrasound. And there again we have the soft tissues as a group, calcified bone as another group, and gases as another group, and we have drastic refractions on bone soft tissue boundaries and very few refractions, but it's the velocity, it's the speed actually of ultrasound that's good. Now, we know that the first thing we have to decide is what are we going to do. Is it going to be just obstetrics and gynecology? That's one possibility. Or is it going to be broader than that, including neonatal brain or neonatal hip? Or is it going to be even broader than that? That somebody else is going to do upper abdomen or echocardiography and so on. Depending on that, we must then have certain properties in our machine. So it's not the same. And the first property that you have to choose is the kind of probe. So if you're going to look through intercostal spaces, you need a sector probe. It must be a sector probe. Like for echocardiography, it must be a sector. For upper abdomen, it can be a sector probe or a convex probe. For obstetrics and the gynecology, it's the same. You need a convex probe or a sector probe for gynecology probe. But for obstetrics, you want a linear probe. For breast, you want a linear probe. For thyroid, a linear probe. For neonatal hip, a linear probe. Okay, so this is the logic, because it's the format of the image, it's the format actually of the acoustic window through which you're looking. So that's the thing that you decide, and then from there on you work up to the machine, the big box, which really is less characteristic for the whole process than the probe itself. Now you have the formula in here for reflection and reflection. You're really not going to calculate this reflection in your lab. But because this is the course in physics, you must know what to do with such a formula. If you have numbers, certain numbers, and you have a simple formula here, which is Z2 minus Z1 divided over Z2 plus Z1, then you just plug the numbers into that. And it's very instructive in putting the numbers into that, because if you get very large differences among the Z2 and Z1, you will see that in fact everything reflects, irrespective whether you are going from air into the body or into the soft tissues, or from soft tissues into gases. You must decide on the type of focusing. It's yourself who decide on the type of focusing. Do you want a fixed focus or a flexible focus? If you could get it to the same price, then the answer is always a flexible focus. Oh, of course, you want an annular array or a matrix probe. That's what you want, for sure. Except that for a matrix probe you need $20,000 more. For an annular array you need $6,000 more than for a fixed focus single probe. So if you have it, then you can have it, if you have the dollars. And it's as simple as that. The logic is not always simple, because if you have two probes, like you have one probe with a focus at 9 centimeters for adult abdomen, and you have a probe with a fixed focus at 4 centimeters, and one of them breaks down, then you can still do the rest of the work with the other probe. If your flexible focus probe breaks down, then you can't do anything more, and it costs twice the money. So it depends exactly what's your premium in your practical work. But you must know that there are fixed focuses, that there are lenses, that there are acoustic mirrors, that there are electronic focusing possibilities. You must know that, because you are the people who are going to choose. Now, about Doppler, one basic limitation you absolutely must know is that at 90 degrees you can't measure. You cannot measure. So, if your aim is to measure the speed or the velocity of that flow, it may not be 90 degrees. You can see the positivity at 90 degrees because you're seeing the turbulence, so you're getting something in terms of positivity. But for velocity, 90 degrees is definitely useless, totally useless. That's about it. Oh, one thing. Ultrasound is with real-time ultrasound is absolutely this is very good for guiding procedures, to guide a puncture. I think you've seen it. Have you seen it?
Yes.
Right. Now, you must be aware of what is your main problem in doing it. Yes, because it's too deep. So if you go with your needle through that plane like that, you see something on the skin, but it's not the tip of the needle. So that's your main problem. If you know that is your main problem, but the needle is not all that visible. You don't see it as a needle on the skin, of course. Just see it as a moving dot. But you do see, to a certain extent, or sufficiently, let's say, for practical work. But what is your main problem is that you miss this scanning plane. So if you know that is your problem, then you know what to do. Well, while you are doing it, maybe somebody else would hold something or manipulate the machine. But while you are doing it, and you know that the main reason why you can miss it, you may miss it, is that you are not in the right plane, that means that you should maneuver a little bit with your probe, just a little bit, and that requires good sense in your fingers to manipulate your angle just a little bit to see whether you're actually seeing the whole needle or the tip of the needle, or you're seeing some part of the needle which is not the tip. So if you know the problem, you know the solution. And this is the REPA. This is the only things that you really must know. Everything else that you heard from me during these 5 days is something that is good for you to know, but it's not a must. Right? So, any questions?